Today, we are going to dive right into the heart of what makes batteries work, what makes our nerves fire. We're talking about electrochemistry. And we're going to tackle this as a story in two parts. First, we'll look at the incredible potential for energy that's just locked up inside chemicals. And then we'll see how we measure the actual flow of that energy once it's let loose. All right, so let's start with something we see all the time. You pick up a battery, it says 9 volt on it, but what does that volt actually mean? Well, in a nutshell, a volt is all about the push. It's the electrical potential, the force that gets things moving. It's really the why behind the zap. So understanding this fundamental push, that's our first stop. To make any sense of this push, scientists had to find a way to measure it, to rank it for all the different elements. Think of it like a sports league table. But instead of teams, you've got chemical reactions. And that league table, it's called the Electrochemical Series. It basically ranks everything by what's called its standard reduction potential. Now, that's just a fancy way of saying, how badly does this element want to snatch electrons from something else? The bigger the number, the stronger its pull. And what's really fascinating here is the sheer contrast you see. I mean, look at this. Way up at the top of the league, you've got fluorine with this huge positive potential. It's the ultimate electron thief. It'll rip them away from pretty much anything. And then, way down at the bottom is lithium, the polar opposite. It's so generous, it's practically begging to give its electrons away. And that difference, that incredible tension between the giver and the taker, is the secret sauce we use to create power. So, okay, we can rank the push. Big deal, right? Well, it is a big deal, because that ranking tells us so much more. Let's look at how this potential actually translates into predicting a reaction's power, whether it will even happen, and where it will end up. See, the total potential of a cell, what we call its electromotive force, or EMF, it isn't just a number. It's like a key that unlocks a really deep understanding of the reaction happening inside. It's almost like having a diagnostic tool for energy itself. So, with this superpower, knowing the EMF, we can figure out 3 incredibly important things. First, the absolute maximum work we can possibly get from the reaction. Second, whether that reaction will even happen on its own. And third, we can predict exactly where the reaction will finally stop. First up, maximum work. This little formula tells us the total amount of electrical energy a cell can possibly kick out. To put it simply, a higher voltage doesn't just mean a stronger push, it means there's more raw energy available to do actual work, like, say, powering the phone in your hand. Next is Gibbs free energy. This is the ultimate test for whether a reaction is just going to happen spontaneously. It's simple, really. If your cell potential is positive, then the Gibbs free energy, or delta G, is going to be negative. And a negative delta G? That is the universal green light in chemistry. It means the reaction is a go, all on its own. And finally, we get to the equilibrium constant. This tells us the reaction's final destination, its end game. A high cell potential means you're going to have a massive equilibrium constant, which tells us the reaction will just keep going and going, almost to completion. The cell's potential literally tells us how the story ends. Okay, so we've talked a lot about the potential for electrons to move, the spark, the push. But let's be real, all that potential in the world is completely useless if the electrons can't actually go anywhere. So it's time to talk about the flow. And that brings us to the second half of our story, conductance. It's not enough to have potential, you absolutely need flow. So how in the world do we measure how easily that current actually moves through something? The concept here is actually beautiful and simple. Conductance is just a direct measure of how easily charge can flow. I like to think of it as a highway for electrons. A higher conductance means a wider, smoother, faster highway with 0 traffic jams. And right here, you can see that relationship crystal clear. Conductance, which we measure in Siemens, is the exact inverse of resistance, which we measure in ohms. One is all about the ease of flow, and the other is all about the opposition to it. They're just 2 sides of the very same coin. But, just saying a solution has high conductance isn't really specific enough for scientists. To compare different solutions in a fair way, we need a standardized measurement. And that's where this idea of conductivity comes into play. This is why specific conductance is so brilliant. To standardize everything, we just imagine measuring the conductance of a perfectly defined cube of the solution. By doing that, we're always comparing apples to apples. We totally remove the size and shape of the container from the equation and get right to the true core conductivity of the substance itself. And we can even get more specific by asking different kinds of questions, like how well does a certain amount of a substance conduct electricity? That's where molar conductance comes in. It looks at the conducting power of exactly 1 mole of something. Or we could use equivalent conductance, which looks at 1 gram equivalent. They're just different tools in the toolbox for making very specific comparisons. So what's the absolute maximum possible flow? I mean, what happens if we could just remove all the obstacles and let those charges move completely freely? Well, that very question leads us to one of the fundamental laws of electrochemistry. This is Kohlrausch's law, and what it says is that if you dilute a solution like crazy, so much that the ions are super far apart from each other, they basically stop getting in each other's way. And at that point, the total conductivity is simply what you get when you add up the conductivities of the individual positive ions and the negative ions. They each just do their own thing, contributing their part to the flow, totally independent. And what's so incredible about this is that it's not just theory. This law gives us a really practical tool. You can measure the conductivity of a real solution you have, then you calculate the theoretical maximum conductivity using the law, and then you just compare the two. That simple division tells you the exact percentage of your substance that has broken apart into ions. It's like getting a powerful peek into what's happening at the molecular level. Okay, let's bring this all home. We've gone from the initial spark of potential all the way to the resulting river of electrical flow. So, what's the big takeaway from this whole journey? Well, we started with the Electrochemical Series, trying to understand the push or the potential that drives a reaction. Then we switched gears to conductivity to measure the actual flow of charge that this push creates. And really, these two ideas, potential and flow, they are the two fundamental pillars of how we store and use chemical energy. And that leaves us with one final thought. The battery that's powering whatever device you're watching this on right now, it's a perfect example of the stance. Its voltage, that's the potential. The current it delivers to your screen, that's the flow. So where else in your world do you see this fundamental interplay happening? Once you start looking for it, I promise you'll see it absolutely everywhere.